Hi everyone, welcome to our class today. Before we start to talk about technical things for the lecture today, I think it is still very important that we talk about the announcements. You can see that on this class, so basically for the week 13, for the rest of the plan is that this is going to be, for the rest of the semester, the plan is that this lecture is going to be the last lecture that talk about technical details. So in particular, we will talk about approximation algorithms, and I think I will also give a very brief discussion about the course summary. So basically for the last two classes, for the class on week 14, we will have our final presentations, or 10 minutes for each student. And for week 15, we will actually going to have final exam in class. So in particular, I think we have posted an important announcement actually in the course.pqu.edu.cn, and also I have sent corresponding emails to all of you. So this is the important announcement in case you didn't have received. So I just copied this announcement in the chat box. As we just mentioned, this class, I will give the last lecture. Basically for the week 14, notice that there is actually a link. So basically you need to schedule your the presentation time of your final presentation in the next class. So basically each students are supposed to give a talk for 10 minutes. So we have a tight schedule. So this 10 minutes is basically the limit, a hard limit that we need to obey. And we have 1 minute for each student to switch. And actually the final presentation will also take place here on Tencent meeting at the same link and password. So for week 15, as I just mentioned, we are going to have the final exam. And basically, due to the current COVID situation, it is okay for some students to take the final exam online. But if students need to take the final exam online, you must apply that to me through sending an email. So that is very important. And actually, the application must be finished at 1 day before the final exam. So basically, as mentioned in this notice that application for taking the final exam online must be made by December 12th, the end of December 12th. That is basically 11:59 p.m. So that is for the policy for the final exam, and for students who has to take the final exam online and basically has made the application by the time, I will actually send you a link basically at the morning of the final exam to the specific place where you're going to take the final exam. And I made a very detailed regulations for taking the final exam online. So there are some details you can check that you definitely need to follow if you want to take the final exam online. And also another very important thing is about the grading policy. So according to the current situation, student can't take the pass-fail grade for the final grade instead of like typical letter grade like A+, A minus, B+, etc. So by default, students are taking the letter grades, and if you want to take a pass-fail grade, you also need to make the application before the final exam. The same application deadline for taking the final exam. Okay, so that is like a brief summary about the announcement, and you can just check the announcement I just sent in the chat box, and also sent in the email, also at the course.pq.edu.cn. So that is an important announcement you want to know about, like the end of the course. Okay, so is there any question about that? Okay, so if there's no question, let's continue to talk about the thing that we want to introduce today. So basically for the last lecture. So today we are going to introduce the last topic of the course, which is approximation algorithms. So approximation algorithm in general, very important because we have been talking about different ideas of designing good algorithms. Basically like greedy algorithms, the algorithm based on divide and conquer, a dynamic program, a network flow. And also basically for the last two lectures, we have been talking about complexity theory. So in particular, the complexity classes P and NP, and also how to make polynomial time reduction, how to prove NP completeness of problems. And also we talk a little bit about like complexity classes beyond NP. So basically like P space, PH, exponential time, etc. So in general, we know that a lot of problems, they are actually quite difficult. In particular, for a lot of NP-complete problem, it's in general intractable that I think as far as people know for not, basically people know for all of the NP complete problem, there is currently people don't know any polynomial time algorithm for solving them. Otherwise, people will just solve the problem that actually P equals to NP. So for NP complete problems, they are actually quite common. And in general, I mean, people don't, at least currently people don't really, expect to have like a polynomial time algorithm for that. But I think people in general still want to solve some problems fast. So by doing that, people need to think about, okay, for a specific problem, what is the important factors that we actually, maybe we cannot satisfy all the important things, but given some relaxations of some problems, maybe we can give some good results. So this is like in general, to tackle with some very difficult problems in general, maybe we can talk about approximation algorithms. Okay, so let's start. Okay, so we say that suppose we want to solve an NP complete problem. Okay, so we need to think about what is the strategy that here we are going to do. As we just said, in general, for NP complete problem, it's unlikely that we can find a polynomial time algorithm. Otherwise, we solve the P equals to NP problem. So the thing that we actually think about, in particular, we're probably, we have the following factors about like designing good algorithm, polynomial time algorithm. So maybe we probably need to have to sacrifice some of the following. So we say we need to sacrifice one of these three desired features. Okay, so the first point is that maybe we want to solve the problem to optimality. So the second point is that probably we want to solve the problem in polynomial time. And the third point is that we want to solve an arbitrary instance of the problem. It's probably just in general for NP complete problems, we cannot satisfy all of the three desired features here. So maybe we want to talk about, for instance, in general, if given exponential time, you just like you're sacrificing the second point that you probably cannot solve the problem in polynomial time. And I think for some cases, maybe for some specific problems, for special instances, you can solve it very fast. But for arbitrary instances, this bring extra difficulty. So maybe we can also talk about sacrificing the third feature here. So here, the main topic today we are going to talk about is that we want to talk about algorithms that maybe can slightly sacrifice the first point. That basically we want to, for instance, sacrifice a little bit about the optimality. So we say this is probably our target here. So maybe we sacrifice a little bit about the optimality here, but hopefully you can still get a good result here. So in particular, throughout the lecture today, we will talk about some row approximation algorithm. So this row here is just a certain parameter here. Typically, it is a constant, or maybe it is like a function in terms of n, etc. So this row here is just like a factor here, and let's actually formulate everything down here. So in particular, we have want to have like a row approximation algorithm if it's like guaranteed to run in polynomial time. So that would be good. And for the second point is we are going to satisfy basically the third features above. So basically, we can say that we want to guarantee to solve an arbitrary instance of the problem. And for the third point, is specifically about this definition of row here. So what is called like a row approximation algorithm. So in particular, we say that we want to guarantee to find a solution to say within row of the true optimum. Okay, so in particular, we know that actually according to this definition, we actually want to solve the problem. I mean, want to give a polynomial time algorithm and actually can solve for arbitrary instance of the problem. So in particular, I mean, maybe it's because the difficulty of the problem, you don't know what is the true optimum. So basically, maybe you don't know what that is. But on the other hand, I mean, you still need to actually give a guarantee about that. Basically, I mean, as long as you algorithm runs correctly, you're actually going to give a solution within this kind of ratio. So in particular, a note that we are going to make is that we actually need to prove that the solution's value is actually close to the optimum. Even without knowing what the optimum value is. Okay, so this is very important. And in particular, I think basically for the topics that we discussed today, we will actually pay specific attention to, I mean, what is actually assumed and what is actually we don't know. But in general, I mean, for designing a good approximation algorithm, we not only need to show that the algorithm runs in polynomial time and actually can solve arbitrary instances of the problem, but also, I mean, even without knowing what the optimum value is, we can still get like this kind of good guarantee that basically the solution that we get from this algorithm is actually within a certain ratio compared to the true optimum. Okay, so this is like a description of the approximation algorithm that we are going to introduce today. And let's look at the first problem that we are going to talk about, load balancing. Okay, so for the load balancing problem, it is actually a scheduling problem that is, I mean, like a theoretical model for a lot of practical problems. So in particular, we consider such kind of things. So assume that we have n identical machines. And assume that we also have n jobs. So basically some jobs that we need to finish. And in particular, let's say that job J has processing time Tj. So here, of course, that J is among 1, 2 until n here. So about each job, we have some requirement. So in particular, the job J here, I mean, for an arbitrary job, must run consecutively. Or we say continuously. I mean, on one machine. So basically, this is like a scheduling problem. I mean, if you start a job, you must finish that on a specific machine. So maybe you can have some thoughts. I mean, basically having like this job J has a processing time Tj here. Maybe you want to have discussion. I mean, arrange it as a specific machine or start at a specific time. But once it starts, it must finish. So basically, this is very important that we assume that each job must actually run continuously on one machine here. And of course, I mean, because we are talking about a scheduling problem, so another important requirement is that a machine can process at most one job. At a time. So one machine cannot process two different jobs at the same time. Okay, so there are some further annotations that we are going to use here. So let's say let's use the J of I to be the subset. Assigned to the machine. So here, I mean, we typically in this load balancing problem, we will use the letter J for a job. And actually the J here is taking amount from 1, 2 until n here. And we use I to represent machine. And actually we have m machines here. So basically we know that actually I is taken from 1, 2 until n. And we use J of I to be the subset of jobs assigned to machine on I here. And then it makes a lot of sense. Actually, we define the load. The load of the machine I is basically denoted. We denote as Li to be the summation of all the J in J of I. So this is a load of the specific machine here. And we have a definition called the make span. So we say the make span is the maximum of the maximum load on any machine. So we use the letter L to denote the make span here. L is just the maximum of all I among all the Li's. And the goal of the load balancing problem is to assign each job to the machines. And actually, we also, of course, we want to minimize the make span here. Okay, so this is the statement of the load balancing problem. So you can probably see that this load balancing problem, it is actually quite natural. I mean, this is like one of the most basic models among a scheduling problem. So in particular, we have these machines and we have the jobs, and we want to, assign the jobs to the machine. So the main assumptions that we gave here is that once the job starts, it must finish on a specific machine. And also the machine can only process at most one job at the same time. So we after having this kind of assignment, basically for each of the machine, we calculate all the jobs that are assigned to this machine and basically the total length of the processing time. The make span is defined as the maximum load on any machine, and basically the goal of the load balancing is that we want to minimize the make span as small as possible. Okay, so is there any question about the definition of the load balancing problem? Okay, so let's think about how we can actually give a good algorithm for the load balancing problem. Let's maybe just think about something a little bit naive that in general, for instance, let's when talking about something naive, I guess maybe we're going to talk about some greedy algorithm, because like the greedy strategies, they're typically quite straightforward. So in particular, in terms of like a greedy strategy, what is the point that we can make it to be greedy here? So let's assume that in general, think about, this kind of problems that what is like going to be expensive for the load. It is typically that the job that have like a large processing time. So we definitely don't want to have the case, maybe for instance, a few jobs, they actually take a lot of time, but actually they are, for instance, in the same machine. So typically we want to make some kind of average. Hopefully, if like one machine that actually process like a long time taking job, maybe hopefully for the next, maybe it is taking like a job that taking less time. Or in general, maybe at the current time, maybe you have already assigned a few jobs. If you have like a new job to assign, hopefully it is assigned to like a machine that actually, for instance, like the current workload is as small as possible. So this is like in general, if you think a little bit more about this load balancing problem, maybe this is something that we can actually pursue here. So this is actually already giving some idea, and actually let's make this a little bit more formal here. So as we just discussed, like a natural greedy strategy. Is actually going to give us a good algorithm, and this is actually called a least scheduling algorithm. Okay, so what is the definition of the list scheduling algorithm? So in particular, let's say that we consider n jobs in some fixed order. So let's just say that all of the jobs are given, to us in a specific fixed order. So an algorithm that we can probably do here is that we can assign a job J to the machine. Whose workload is the smallest so far? So this is a very straightforward greedy strategy that we can use here. Or maybe we can actually write down the algorithm, the list scheduling algorithm as follows. So list schedule. So of course, we are going to have the parameters m and n here. So as we have the jobs in some fixed order, so let's just say that the jobs, they're actually having processing time T1, T2 until Tn here. So we just give them as the inputs here according to this order here. So the algorithm is going to look as follows. At the very beginning, for the initialization, so for I from 1 to m, so initially all the machines, we actually know that initially the load is 0, and initially all the sets they're actually empty set. And after that, we have this specific order of all the jobs. We just go from the first job until the nth job. So for J from 1 to n, we do the things as follows. So we just take I to be the argmin of all the LK here. And then we update the JI here to be the set JI union by J here. So basically, we just put the element J here into the set JI. And also correspondingly, we need to update LI here. Because we have put the job J here. So basically, we need to update LI to be LI plus TJ. Okay, so let's actually give some annotations here. So in particular, for the first line, in the for loop, so basically we say I equals to argmin of LK here. So this is basically saying that actually the machine I here, it actually has the smallest load at the moment. And basically, after we have a finding of this I here, so basically we can assign job J on machine I. And of course, we need to update the load of machine I. Okay, so this is the very straightforward scheduling algorithm here. So what is the implementation time of the list scheduling algorithm? So does anyone have any thoughts about this? What is the implementation time? So the implementation time here is actually O n log n here. So by a heap. So recall the heap data structure that we introduced at the beginning of the semester. So basically, for the heap is basically we have the capability that having a heap, we can each time output the minimum value here. So that is a specific reason that maybe we want to use a heap data structure here. Because basically for the first line in the for loop of J here, each time we are actually finding the minimum value here. So basically, this is very easily to be maintained by a heap here. And basically, the update cost of a heap inside each iteration is going to be log n. And we have n jobs in total, and overall, the implementation time is going to be O of n log n here. And actually, we can implement this by a heap and actually finish what we actually do. Okay, so this is basically a first step that for this sounds like, in general, basically this load balancing problem. This load balancing problems is actually NP complete. So maybe you can think about how you want to approve this. But I can tell you that this load balancing problem is actually quite difficult in general. So in particular, I mean, we don't expect to actually find a good algorithm. I mean, like a polynomial time algorithm that can always find the optimal solution. But let's say that we want to use this scheduling algorithm, and basically, I mean, this is really a straightforward greedy strategy, and the algorithm is actually quite simple here. And actually, the implementation cost is also a relatively good. I mean, it's only O of n log n using the heap data structure. So maybe you want to have a good understanding about like what is the behavior of this algorithm, and in particular, I mean, how far are we from the optimal solution here? So this needs actually a little bit more discussion here, and actually let's give a little bit more proof here to understand what is the value here, that actually how far we are from the optimal solution. So in particular, we denote basically denote, let's say, the mix span of the optimal solution. This is not right. So the mix span of the optimal solution as L star. So there are some actually very brief observation that we can make. So lemma one, we are going to know that actually the optimal mix span basically this what L star is actually going to be at least the maximum J of all the TJ. So basically the maximum of all the processing time of all the jobs here. So in particular, I guess this is lemma. I think this is just trivial because it's just that some machine actually must process the most time-consuming job. I think this is a straightforward lemma here. Let's continue our, brief observation here. The second lemma. The second lemma that we want to argue here is that actually the optimal solution, basically the optimal mix span, still this value of L star. It must be larger than 1 over n with the summation j from 1 to n TV. So what does this mean? I mean, I guess this is also something a little bit straightforward. So in particular, the total processing time. I mean, we just sum up the processing time of all the jobs. It's just this value, summation of j from 1 to n TG. So this is just the overall, the total processing time among all the jobs. So I mean, the average, I mean, we definitely know one of the jobs, so one of the machines actually must do at least average of this. Which is basically this. Okay, so any question about these two lemmas? I personally think that probably these two lemmas, they are actually quite straightforward. I mean, on the one hand, this L star is actually should be at least, I mean, the maximum of all the processing times. And also on the other hand, we know that this L star is actually going to be at least the average of all the, of actually the total processing time. So that is actually given the lemma 2 here. But actually what I'm going to say below here is something much less trivial, and actually gives the approximation ratio of this list scheduling algorithm. So this is originally due to Graham. And actually Graham proved that actually the list scheduling algorithm is a 2 approximation. So we will actually use these two lemmas, which actually look at the first hand very trivial to prove something very non-trivial, that we actually prove that this scheduling algorithm actually a good approximation algorithm. So in particular, how are we actually going to do that? So basically, we are going to utilize some part of the algorithm. That in particular, we are actually using a greedy algorithm, and we really want to utilize the greedy property of this algorithm to help us. So in particular, we are going to make the proof as follows. So let's consider the load Li of the bottleneck machine. So here we call the machine a bottleneck machine. Where actually let's denote the bottleneck machine to be the ith machine. Where actually it is the machine that actually reaches the max span. Or you can say like the machine that takes the longest time in this scheduling. So we are always going to have such kind of bottleneck machine that actually takes the longest time and actually reaches the max span here. So we can make some further notations here. So after all, if a machine takes the longest time, there are definitely going to be some jobs in this machine, definitely. So let's say that the job K is the last job. Scheduled on machine I. Okay, so in any case, as long as we have a bottleneck machine, so basically we are going to have a last job, on this machine. So this is actually a point that we are going to use the greedy strategy. So in particular, by our greedy strategy. So by our greedy strategy, so when job K, the job that is actually the last job scheduled on machine I here. So when job K was assigned to machine I, we know that actually I has the smallest load at that time. This is due to how we actually give the algorithm. If it is assigned to the machine I at that time, basically we know that due to the greedy property, actually I has the smallest load at that time. So in particular, we know that actually its load before assignment is going to be Li. The final workload minus Tk here. So in particular, we know that basically this is going to imply that Li minus Tk is actually going to smaller than Lj for all when smaller than J smaller than M. Here the J here can also be I here because clearly Li minus Tk is smaller than Li here. But actually this holds for all of the machines here. So maybe let's actually draw a picture like this. So in particular, let's assume that we have like the following schedule. So here maybe we have like machines here. So we have some machines here. And basically this is our schedule here. So assume that this is the ith machine, and basically maybe for instance, ith machines looks like this. And maybe finally it has like this job. And this is actually the bottleneck machine that we have been talking about. So we can also take a look at the other machines. So for instance, maybe we have like a machine like this, and maybe like this. So in particular, we want to have a specific understanding about this is basically going to be the K that we talk about. Basically the last job that is assigned to the machine I here, and actually the machine I here is the bottleneck machine that we have been talking about. It must be the case, looking at the other machines. It must be the case that at the time, basically this is the time Li, and this is the time Li minus Tk. So it must be the case that at the time Li minus Tk here, the other jobs, I mean the other jobs must have already taken longer time like this. So basically, the other machines has already been over this, or otherwise maybe for instance assume that maybe this is shorter like this. So if you have like a job like this, so but this is actually going to violate the greedy property, because instead, I mean, if this is the case, you have should have assigned the job K here. But this is actually not the case, and we are talking about, I mean, the bottleneck machine I here, and actually the last job, the kth job is actually assigned to the machine I here. So this is definitely not going to be the case. And actually, I mean, looking at this, we are just going to know that maybe the other jobs, maybe for instance, this machine is going to look like this, like this machine is probably going to look like this, etc. And nevertheless, I mean, for all of the machines, we are always going to have this inequality that Li minus Tk is going to be smaller than Lj for all of the j between 1 and n. So this is actually a key observation that we actually make for the greedy algorithm, this at least a scheduling algorithm. So in particular, we say that actually we can sum over, excuse me, actually I think it just frozen. So let's sum over all of the j here. So in particular, we sum the above inequality over j, and actually we divide by n. Now we are going to have the following result that actually Li minus Tk is actually going to be smaller than this 1 over m with the summation of all the j from 1 to m Lj. And basically, if you summing up actually all of the, I mean, the load of all of the machine, this on the other hand, I mean, we process all these jobs, and this is actually going to be also going to be the summation. So basically, just looking at this sum here, this is actually going to be the summation just of all of the j from 1 to n of Tj here. So where this is actually the summation of all the processing times of all of the jobs here. So we know that actually, I mean, we have this lemma 2 here, that actually we have already a bound in terms of the summation of all the processing time of all the jobs here. So in particular, I mean, basically we know that this is actually going to be a smaller than L star. And this is actually just our lemma 2 here. And after knowing this, we know that actually we have the fact that Li equals to Li minus Tk plus Tk. I mean, Tk is only one of the jobs. I mean, basically by lemma 1, we know that it's actually smaller than or equals to L star. And on the other hand, we also know that Li minus Tk, I mean, as discussed above, it is actually also smaller than or equal to L star here. So in total, this is 2 times L star here. And basically just finishes the proof. Okay, so basically this is the proof that the least scheduling algorithm is a two approximation algorithm. And in terms of the proof here, the discussion here, you can probably see that the point that I was mentioning here, so the note here. So we actually need to prove that the solution's value is close to the optimum, even without knowing what the optimum value is. So throughout the algorithm, I mean, we have no assumption about like what specific value L star is, but we know that we actually have an optimal solution. And having this optimal solution and compare that to the greedy algorithm. So basically, there are definitely some good things that is going to be satisfied for the greedy algorithms, in particular as this figure shows here. So the good thing that this greedy algorithm must satisfy is that basically, as long as you look at the bottleneck machine I here, and basically this bottleneck machine is going to have a last job. The last job, assuming it is going to be a job K here, we are going to know that actually Li minus Tk is going to be smaller than or equal to Lj here. So this is the important point that using this greedy strategy that actually the algorithm is going to satisfy. And as long as this is actually satisfied, we know that we can actually have a good guarantee compared to the optimal solution. And we just show that the value Li here, I mean, because we know that the value Li is the largest among all the loads here. So we just know that the solution we get is actually, the longest time among all the machines is just at most 2 times L star here. And actually, we are getting a good approximation algorithm, two approximation algorithm for this load balancing problem. Okay, so is there any question about the proof here, about the argument that actually we have a two approximation algorithm for the load balancing problem? Okay, so this is just a very quick argument that actually we give a good algorithm that in particular for the load balancing problem, we have a two approximation algorithm. So maybe we want to be actually, assume that we are not satisfied with this. So maybe we want to have like a further question that whether we can improve the approximation ratio. So for instance, maybe we want to ask whether approximation ratio can be even smaller than 2 here. So one thing that maybe, thinking about the algorithm, the strategy that we use here. So maybe the strategy that at least a scheduling algorithm is already quite good. But there is another thing that maybe we can actually utilize. It's about actually the point that we can actually, we hear actually the algorithm, we assume that we have a fixed order here. So maybe it is the point that, in general, for like whatever algorithm, whatever like a job sequence, I guess this is quite good that you can get like a two approximation algorithm. But assume that given the knowledge of all the processing times, T1, T2, until Tn here, maybe you can have, you don't always have to, process this in some fixed order. So assume that you know like the processing times, maybe you consider some kind of a specific designated order, and hopefully under this kind of order, you can give a good algorithm. So this is a specific point that we can actually tackle with. And in particular, think about the intuition here. So the intuition here is actually, in terms of this proof here. So actually for this TK, so we just, for this TK, we just reduce it to L star. Because in the worst case, maybe this K just is the job that takes the longest time. But ideally, maybe for instance, hopefully if at the last, the jobs in your hand, hopefully they take a relatively short time. So this is probably, in terms of this, hopefully like this intuition, maybe we want to have like the last jobs to have short time. Or put it in another way, it's probably maybe at the beginning, you're okay with taking some longest jobs. Because after all, you got to finish them. You got to finish the jobs that taking the longest times, etc. So you got to deal with them. So maybe, in terms of this kind of discussion, like a kind of a natural thing here is that maybe in particular, maybe about like the question, how about like a designated order? As maybe we can have the choice here that in particular, if you can have a choice about what is the order, of the job of processing all of the jobs, is that maybe we want to consider something called the longest processing time. How we call this LPT. So in particular, at the beginning, we can just feel free to sort the n jobs in descending order. Of processing time. And then run this scheduling. Or formally speaking, the algorithm, the algorithm LPT list scheduling with the input M1, Mn, T1, T2 until Tn to be something like this. So the first line is that we want to sort jobs so that T1 is larger than T2, larger than etc., larger than Tn. We just sort the processing time of all the jobs. And after having this, we just then run the list scheduling algorithm. And n on T1, T2, until Tn. Or put it in another way, you can just assume that for running the list scheduling algorithm, you have already have like a descending order of all the processing, all the processing time of all the jobs here. So this is the idea. I mean, as we just discussed, this is actually coming from this greedy strategy that hopefully at the end we have like a short processing time for the jobs, or maybe for the jobs that actually are taking a longer time, we just process them at the beginning. So this actually the reason that we comes from this LPT strategy, that we first process the jobs that are actually having the longest processing time. Okay, so this is the intuition, and let's talk about some further detail here. That in particular, what is the approximation ratio of the algorithm based on the longest processing time? So the first observation. The first observation that we are going to make here is that actually, if we have at most m jobs, so assume that we have at most m jobs, where m is the number of machines here. Then basically we know that at least scheduling is optimal. It is actually the optimal solution. So why is this the case? I guess this is actually quite straightforward, because for the least scheduling algorithm, I mean, you always assign your current job to the machine which is actually having the smallest workload at the moment. I mean, if the number of jobs is at most m here, you always have like an empty machine, and basically the situation that we are going to encounter is that each job is actually on its own machine. And actually, this is the optimal way, because you after all need to process the job taking the longest time. And the next thing that we are going to talk about, I mean, basically we know that for the least scheduling algorithm, that basically for the situation that they are at most m job, this is just like a very simple case. So the next case that maybe you want to be a little bit more careful is that maybe assume that we have at least m+1 jobs. You want to think about what we can argue here. So we are going to show that actually the L star here is actually at least 2 times Tm+1. So recall that to this Tm+1 is actually the time that actually in this order here. So this is basically, I mean, after we have arranged, I mean, basically we have sorted the time according to this descending order, T1 larger than T2 larger, etc. So this m+1 is specifically the m+1 element in this kind of descending order here. So basically, we're going to show, I mean, if I have a lot of jobs to finish, in particular, assume that if there are at least m+1 jobs, we are going to show that the value, we are going to show the value of the optimal mixed span L star is actually at least 2 times T m+1 here. So I think we can give this proof. I mean, this is actually straightforward, and then we can take a break. So in particular, the proof is actually going to be finished by the pigeonhole principle. So in particular, I mean, among the M1 most time-consuming jobs, I mean, the top M+1 most time-consuming jobs, they are going to be, I mean, since we have already ordered them into this descending order T1, T2, and TOT M+1, we know that actually at least 2 of them are actually in the same machine. This is just due to the pigeonhole principle. So this is going to just suggest that the total time on this machine is actually at least 2 times T m+1. And this is just going to imply that L star is at least 2 times T m+1. So this is basically a lemma that we can observe. I mean, if I have a lot of jobs here. So the next theorem that we are going to prove, I mean, after we take a break, I mean, let me finish writing down the statement, is that actually the LPT least scheduling algorithm is actually 3/2 or like a 1.5 approximation for the load balancing problem. Okay, so is there any question? So if there is no question, let's take a 10-minute break and let's come back at 10/4 here.